Hi guys, today we're going to talk a little bit about derivatives and differentiation and how calculus starts to play a role in physics. And I had a little bit of a PowerPoint, but I think I'm going to skip it, and I think we're just going to do some examples because the more practice, the better. Some of you guys have already seen this because you're in Calculus BC, and some of you guys are in AB and you haven't gotten here yet. So I just want to remind you guys that I am not a math teacher, not a calculus teacher. I will explain to you the bare minimum that you need to understand in order to do your problems and your homework. But if you have specific questions, the best I can say is just wait patiently, and eventually your calculus teacher will explain this in more detail. Okay, so last year we did a lot of work with motion graphs, and you were not aware of it at the time, but we were doing calculus. I didn't call it that, but we were. So last year we learned that for a position time graph, the slope of a position time graph is your velocity. So if I have a position time graph that is a function like this, curvy, we were all taught, oh, that means the object is accelerating, which means that the object's velocity is not constant. The object's velocity is changing. So here is your velocity time graph, and we were taught that the velocity time graph slope is your acceleration. So here would be our acceleration time graph. I'm sorry all of this is so tilted, guys. Do better on the next page. Your acceleration time graph would be a straight horizontal line. So, like I mentioned before, you were not aware of it, but this is essentially calculus. Now, Isaac Newton invented calculus to describe physics, so the two disciplines are very interrelated. It's very difficult to do physics without at least a little bit of calculus. So the first concept we're going to talk about, we'll come back to these graphs in a second, but I want you to keep these in mind for what we're going to discuss. So the first concept we're going to talk about in calculus is differentiation and what it does and how it helps us. So you guys were taught that slope is the change in y over change in x, or more specifically, how quickly y is changing for each increment that your x changes. So if we have a slope, or if we have a line that is a linear relationship or a linear function, well, your slope is constant, and this is very easy to find out. But if you have a function, or if you have a graph whose slope is not linear and it is not constant, let's say you have something funky like this, well, now it's not so easy to figure out how y changes with x, and so this is when the concept of differentiation or calculus comes in to help us. And so when you have a function that looks like this, the slope is not constant, right? So if this is our graph, f of x, we'll just say, then the slope of this graph, the only answer for the slope is to say that the slope has to be another function. It has to be another equation. It can't just be a constant number. So I'm going to show you guys the first power rule, and then we're going to go back to our position time, velocity time, acceleration time graphs and talk about how that works. So the first rule we're going to do is a power rule. Oh, I'm sorry, I guess I should finish this explanation up here. So to find this slope function, we have to do differentiation, or we have to take the derivative of this original parent function. We call it the derivative. I hope I spelled that right. Okay. So the first rule we're going to learn for derivatives and differentiation is called the power rule. This is the most common rule that you guys will encounter in my class. There are a few others that hopefully your calculus teacher will show you, but for right now, let's stick with the power rule. So the power rule says that when you have a function that looks, let's say, some constant, x to some power we'll call n, the rule says subtract 1 from the power and multiply the function by the new power. Oh, sorry, by the old power. So let's plug some numbers into here and let's just practice. So let's say y equals 4 is our constant, x to the third. So the power rule says subtract 1 from the power. So when we take our derivative, so we always do dy dx, this means the derivative of y with respect to x, which becomes important when you start having multiple variables in an equation. We're only going to care about all of the terms that have x in them, and we'll do some examples of what that means and what that looks like in a second. So dy dx, so we're going to subtract 1 from our power, that's 2, and we're going to multiply our function by the old power, which was 3. And so in front of here, we're going to still have our constant times 3. So dy dx then becomes 12x squared. So this is a way of saying this is the slope, the function for the slope of this original parent function. So let's go back to our previous page and just talk about how this fits into what we already know about physics. So let's make up a formula for this. We know that it's a quadratic or a power relationship. So let's say that this is y equals 2x squared. All right. So I told you that whenever acceleration is changing like this, you have a constant change in velocity. So this is what your velocity time graph looks like. So this equation could very well describe this graph. So let's take dx dt, and oh, I'm sorry, this should be x, and this should be t. I'm sorry, that was poor explanation. Let's do dx dt. So we're going to subtract 1 from the power, so that gives me t, just t to the 1, and then 2 times 2 is 4. So over here, our equation for this line, dx dt, is velocity equals 4, not 2, 4t, which is a perfectly acceptable equation for this line. So then if I take this expression and I take the derivative of it one more time, dv dt, well, t to the 1 minus 1 is 0, so t to the 0 is just 1. And then multiply the function by the old power, which is 1, you get dv dt equals 4, which is, again, a perfectly acceptable equation for this line. So, like I mentioned before, you guys already are familiar with the graph portion. We just got to slap the calculus down on top of it. So, what this means, definition-wise, velocity is the derivative of position function, of your position function, and acceleration is the derivative of your velocity function. Now, why didn't I do this with you guys last year? Well, because, oh wait, one more thing. Another way to talk about acceleration is to say acceleration is what's called the second derivative of position function, because I would have to take the derivative of my position function here, and then take my derivative of that one more time to find whatever my acceleration is. So, second derivative of position function. Okay, we're going to do some more examples here in a second. But why didn't I do this with you guys last year? Well, number one, you didn't have the math chops yet. And the second thing is that, why didn't I do this with you guys last year? because a lot of what we did last year, well, pretty much everything that we did, we dealt with situations that had constant acceleration. So for situations where your acceleration is constant, you end up with graphs that look like this. And calculus is not really needed unless we wanted to actually find the equation for these functions, but I never asked you for that. And so calculus isn't really needed. Instead of using calculus, we can just use our good old kinematics to solve for situations where we have constant acceleration happening. So that's why I didn't really talk too much about this last year with you guys, but now you're at a position where, or a point, where things might not really have constant acceleration, right? That constant acceleration idea is not very reasonable. It's not very realistic. This really only happens whenever you're dealing with situations of gravity. And sometimes not even then, because if an object is in free fall and it reaches terminal velocity, eventually there's no acceleration at all, so that acceleration has to slowly be decreasing. So this constant acceleration parameter is just not very realistic. So we're going to try to start investigating some real kind of scenarios, and to do that you need the calculus, because your acceleration will not be constant. It will be a function. Okay, so let's do a couple of examples of some calculus here. Let's give some functions for our math. So let's say we have a position that is defined as this. And I ask you, what would be the velocity and a acceleration at 2 seconds? Well, this gives us our position as a function, so that should be a big red flag to you that I need to find a second function that describes my velocity. So I'm going to take the derivative of x with respect to t. I'm going to use my power rule. 3 minus 1 is 2, and then I'm going to multiply 6 by 3. That's 18. So this is our formula for our velocity. So to figure out my velocity at 2 seconds, I would plug in 2. 18 times 2 squared equals 72 meters per second. Okay, so now they want us to find our acceleration. So now we're going to take our derivative of our velocity with respect to time, and 2 minus 1 is just 1, and then 18 times 2 is 36. So our acceleration at 2 seconds is also 72. That was weird. So this is how this would work in like this kind of function. So let's do a couple of more examples of the power rule, ones that aren't quite like that. So x, let's do 4x cubed plus 6. Okay, so now I'm going to add this little constant over here. So same thing, let's find our expression for our velocity, dx dt. So this is what I was, oh crud, this is supposed to be x. I mean, sorry, this is supposed to be t. Sorry, guys. This is kind of what I was saying earlier, that you're only going to use the power rule on the parts of the function that actually, the variables that have t in them. So dx dt will give us velocity, which is t squared times 12. Now, there's not a t over here in this second term, so I can't take the derivative of it, so it just drops away. It's not there. The derivative of a constant is 0. Of constant equals 0. Okay, and then again, one more time, dv dt to find our acceleration function will be 24t. All right, let's do one more. X equals 3t squared plus 6t. Actually, let's do this. Little different. All right. So let's say you had a big function that describes your position like this, and I ask you for your velocity at a particular time, or your velocity function. So I'm going to go through and I'm going to take the derivative of x with respect to t. For every variable that has a t in it, we'll do the power rule. This guy over here is a constant, right? So his derivative will just end up being 0. So the first one will be 9t squared 12t. Now this guy, he's power 1. 1 minus 1 is 0, so t to the 0 is just 1. And then 1 times 4 is 4. So here is your expression for your velocity, and then we do it one more time. To find our acceleration, we get 18t plus 12. All right, a big question last year was, I don't know when to use calculus. A good hint is anytime they give you a function to describe a variable, you will need to either derive it, take the derivative of it, or integrate it, which we're going to talk about integrate in the next video. All right, I hope this was helpful for you guys, and I'll see y'all later.